Welcome to Science Unwrapped, which is brought to you by the College of Science here at USU. I'm Charlie Torrey from the physics department. I'll be trying to keep this thing rolling tonight for you. This is the first Science Unwrapped of the season, so I'm glad you came. Each year we have a theme, and this year's theme is called Building on Basics. What that means is our speakers, generally speaking, will be taking some very basic scientific ideas and principles and trying to show you how those feature in our understanding of complex phenomena in the world around us. I should tell you in that regard that the next Science Unwrapped is October 6th. There, Professor Dalton from the Geosciences department will be showing us how to tell time using the fossil record. So if you dig fossils and stuff like that, you might want to check that one out. Since this is the first Science Unwrapped of the season, maybe I should make sure we thank everybody that's here. Of course, our speaker was gracious enough to prepare this presentation for us, but College of Science has supported this activity for, 14 years? Is that right? Yeah, 14 years. And we have a whole bunch of volunteers that make this thing go, both running this presentation and also outside in the building with a lot of displays and activities that you can participate in after the talk. So we're very grateful to all of them for all they do. And of course, there's also the Science Unwrapped Committee, which organizes this stuff behind the scenes. Who has not been to Science Unwrapped before? Well, welcome. This is great. Let me tell you how we do it. There will be about a 40-minute presentation, something like that?
30.
30? 30. Very civilized. 30-minute presentation. Hold your questions, please, till the end, and then we'll have 10 minutes or so for questions and answers. Then you're free to leave. You can leave and explore all the fun out in the building, or you can come down and talk to our speaker with additional questions and get to know him a little bit. So I hope you enjoy that. This room is kind of noisy, so anything you can do to keep the background noise down will be useful, especially since sound is going to be a big part of how we understand wave phenomena tonight. Okay, maybe I should just tell you about the speaker. We have Dr. Jon Meyer, who is the Assistant State Climatologist at the Utah Climate Center here at Utah State. Jon has been, I would characterize him as a weather geek from a very early age. I think that's fair. Yes. From a very early age when he was growing up in Colorado, he tried to experience every weather phenomenon he could find. I guess there's one still in your bucket list. He would like to have a look at a tornado. So if anybody has one, you can let him know. His love for weather and climate took him to University of Northern Colorado. Is that in Greeley?
Yes.
In Greeley, okay, in Colorado, Greeley, Colorado. Got his BS there in 2008. Went on to get his master's degree, graduate degree, again in climate and weather science at the South Dakota School of Mines, 2010. Then came to USU and got his PhD here in 2016, again in climate and weather and modeling. And I guess you've been here ever since?
They can't get rid of me.
That's right. And it's our gain, of course. There's one other thing I should tell you about him, since I don't think it's going to feature in the talk. And I even brought my own exhibits. So besides being an expert in all things weather and climate, Jon is also an expert in something perhaps even more important, which is the crafting of high-end hot sauces. So this started as just sort of cooking for friends in the kitchen, more or less, but became kind of a business. And now you can go and get these things all over the country. I have my two favorites. What do I have? I have the Wonder Tonic and my very favorite, the King of Sting. He started this business called Bear River Bottling Company and took it to become a national award-winning operation, and you can just get these sauces everywhere. They're really, really nice. So if you love weather and you like to feel the burn, you should definitely try it out. Okay, that's enough for me. I'll let Jon tell you about the fundamental scientific principle of waves and how it controls Utah's climate. Thank you.
Yeah, don't forget those. When global warming isn't hot enough. Thank you all for sharing your Friday evening and braving the excellent early fall weather that has graced the Utah landscape this week. Thank you for the introduction, and thank you to all the committee members and everybody who has been boots on the ground to put this series together, and the amount of work that it takes to do this is pretty phenomenal. It's a bit intimidating to be the first out the gate and kick the series off, so I hope we have a fun time tonight. We are going to be explaining why our seasons are different from year to year, a fairly complicated topic for climate scientists that have sort of been a challenge to understand scientifically and predict going forward. We're going to use the more simplified topic of waves, sound waves specifically tonight, to explain why seasons are different from year to year. All right, tonight's adventure, we've got 5 different parts that we'll talk about. The first one is the basics of seasons. We're all just going to introduce the idea of why we have seasons, get everybody on the same page there. That'll be the simple part. We'll complicate that a little bit by talking about climate cycles that are operating across the planet on any given year, how that can affect the seasons. We'll simplify things again and introduce some of the jargon and terminology to understand waves, how we can talk about them going forward. And the thing I'm most excited about tonight is watching sound waves. We've got an excellent collection of some climate scientists who are also musicians in our program, and they've brought some of their instruments, and we've got a way to visualize the sound waves that we hear, and that's what I am most excited about talking about tonight. And then we'll wrap everything up with how the climate cycles end up affecting the seasons once we've got all the information that we need to put those pieces of the puzzle together. All right, the simple stuff. Why do we have seasons? It's something that is introduced fairly early on in our education system, the idea that Earth's spin is tilted. About 23.5 degrees off axis. We're a little bit wobbly when we rotate and orbit around the sun. I couldn't resist the sunglasses icon here. I think if you ever have drawn the sun, you've probably done one of these icons. Ironic that the sun needs sunglasses from itself, but fun little image there that nowhere close to the actual reality of what our sun looks like. This is a satellite perspective of the sun. If it will play here, got a lot of loops and animations. Different. All right. There's our sun. Would normally have been spinning. But as we orbit the sun, the most intense energy shifts between the northern and the southern hemisphere, thanks to the tilt of the Earth as we orbit around. This is my favorite animation. I'm really happy that it is animating here. This is a 1-year time lapse from space, satellite 23,500 miles above the surface of the Earth, looking down at the Earth over a full year. And you can see the illumination across the seasons, the northern hemisphere to the southern hemisphere. And as the sun's direct energy moves from hemisphere to hemisphere, we get more or less energy, and that drives our summers and our winters and the transitions between, which we are right on the border between our seasons at the moment. And so that's why we have seasons. Our winters are cold because we're getting less energy from the sun. Our summers are warm because we're getting more energy from the sun during times of the year. So I love that little animation that shows how we receive different sunlight throughout the full annual cycle. Here in Utah, we've been measuring weather and climate for almost 130 years. Right next to Aggie Ice Cream is the state's oldest weather station. It's been measuring since 1893. Some poor intern has been spending their mornings. We've got a couple of them have done that and done their duty for the climate observations. But when we look at 125 years of climate observations across Utah, we average over an entire season. This is what it looks like. So this is The average Utah temperatures, so all of our weather stations across the state over the last 128 years, for April, May, and June. This is our spring average temperatures. And every little dot in the orange line wiggling up and down represents a single season's average temperature for that April, May, and June. The black line that's rather flat is the average across the 20th century. About 55 degrees is our average April, May, and June temperature for Utah. And then that little smooth running green line across that is our smoothed average, so we can see a little bit more of the cycles that control the ups and downs of Utah's spring temperatures. You can see there are years that are above average, above that black line, years that are below average, below that black line. There are periods where multiple years are above and periods where multiple years are below. This is the heartbeat of Utah's weather and climate for the spring. We can do the same thing for January, February, and March precipitation. So this is our wet time of the year when we're building up a lot of our crucial snowpack. And again, you can see a heartbeat in that running red line across the graph. That represents the wet and the dry phases that influences Utah's climate. We have dry years or wet years. It's also interesting to note that while we have an average here with the black line, it's pretty rare to have a year that is normal. Most years are above normal or below normal. We average them all together and we get some average number. But getting a normal year is actually pretty rare. So these are the heartbeats, the rhythms of Utah's climate. We have years above, years below normal. So tonight we're going to explain what drives this, what shapes the heartbeat and the rhythm of Utah's climate. We're going to do it with some fun sound demonstrations here in a little bit. Before we move on to the more complicated thing, the last little bit of information I want to arm everybody with, we're going to turn you all into amateur meteorologists for a second here, is the importance of the jet stream, which most of our older audience that focuses on the weather forecast has heard the term jet stream tossed out in the weather forecast, wherever you listen to it. The jet stream is one of the most critical aspects of weather and meteorology. That's why it gets mentioned so much in our forecasts. The jet stream is a river of fast-moving air. We call it the jet stream because it exists about 30 to 40,000 feet above the surface of the earth, where our commercial jetliners fly. And it's a very narrow ribbon of this very fast-moving air that at times can approach 200 miles per hour, which is about as strong as the strongest hurricanes will blow. So very strong winds exist up there. They're not always present. Every hemisphere usually has at least one jet stream, but we can have up to 2 jet streams in each hemisphere for a total of 4 across the planet. And you can see it sort of snaking and meandering across as it moves. And it's so important because the jet stream, I like to call it the shepherd of the storms. It's controlling where our weather patterns are going, our high pressures that bring hot and dry conditions, and our low pressures, which bring cold and stormy conditions like we're getting outside today. And the jet stream is controlling that. Another way to think about it is the jet stream is the storm track. It's the highway that controls where the storms go. And so depending on which side of the jet stream you're on, if you're on the high pressure side, you get hot and dry weather. If you're on the low pressure side, you get cooler and stormier weather. And so being able to understand how the jet stream moves around and how it influences weather patterns is one of the most amazing parts of meteorology. It's a challenge that brings day-to-day intricacies in the puzzle that usually really gets excited for all the meteorologists. All right, that's the simple stuff. Let's complicate things a little bit and talk about climate cycles here in a second. Who's heard of El Nino? A show of hands. Yeah, El Nino is one of the most famous terminology in weather and climate. So much so that one of the top 5 Saturday Night Live skits features Chris Farley trying to describe what El Nino means. Comedically fails, but it shows how much El Nino has permeated pop culture. El Nino is the most famous example of something climate scientists have coined a climate teleconnection, which is the biggest word that I will use today, and it will not be on the quiz afterwards. Climate teleconnections describe naturally occurring parts of the weather and climate system where variations in temperature and pressure patterns in one area of the globe influence weather somewhere else. That's the teleconnection. It's a big word, so we can simplify it. If you ever hear me say the word teleconnection going forward, just think about how this is like a telephone and how a climate telephone can connect two different parts of climate on different parts of the world. El Niño is the most famous one. It's a very big and very important climate teleconnection across the planet. It's describing ocean temperatures in the Pacific, cycling between above average temperatures and below average temperatures. And El Niño is the condition where the Central Pacific is above average. It's what we're going into right now and what will influence our winter. And La Niña is the opposite of that, when the Pacific is colder than normal. And you can imagine the sheer scale of this water body, the amount of surface area that this represents across the planet. And as the ocean temperatures go between hotter and colder than normal, it's almost like the ocean is exhaling or inhaling energy from the atmosphere. El Niño is when it's exhaling a bunch of excess heat and energy into the atmosphere, and La Niña is when it's inhaling excess energy from the atmosphere. And so that huge expanse of the planet, inhaling and exhaling energy from the atmosphere, influences the jet stream and how the jet stream moves through the hemispheres. This is a very rough statistical expectation for El Niño winters and its effect across the planet. Just about every continent on the planet has some area that has a relationship with El Niño and La Niña conditions in the Pacific. This is that teleconnection influencing one area's weather and climate based on what's happening in the Pacific. And this happens by influencing how the jet stream moves and where storms do and do not go. So the highway of storms gets affected thanks to Pacific Ocean temperatures. Unfortunately, or maybe fortunately for climate scientists, this is the exciting part, is that there's a lot of teleconnections out there. There's a whole alphabet soup of these teleconnections. Scientists aren't known for being that creative, and most of our teleconnections are giving really boring acronyms. There's a whole collection of them out there. We've got the Madden-Julian Oscillation, El Niño Southern Oscillation, the Pacific Decadal Oscillation, Arctic Oscillations, and a whole lot of oscillations out there. The quasi-decadal oscillation here at the bottom, that's northern Utah's most important climate teleconnection. That's what we watch in the Climate Center to have a measure of predictability for what a given year will look like. But they're all out there. They're all operating together. And this is just a couple of them. All right. Who's confused? That's the most complicated stuff. So let's step back and simplify things a little bit. Let's introduce a little bit of the terminology of wave theory that will help us explain the waves that we're going to visualize here shortly. So right now, we are surrounded by a lot of different types of waves. The most frequently ones that we're used to talking about are light waves. We get to see colors and things as light waves are radiating around us. We have radio waves that help keep our cell phones distracting us during the middle of lectures. It's kind of nice not having a bunch of freshmen to talk to because everybody's focus is up here versus down here. That's a new change for me. This is great. So we have the electromagnetic spectrum and a bunch of different waves like X-rays and gamma rays and light waves and radio waves. And those are all moving about us right now. We have sound waves that are emitting from the speakers and moving through the air into your ears so you can hear me talk. So we are constantly surrounded by waves. We're going to focus on sound waves for most of this, but we'll use light waves here because that's a very familiar concept. Here we have a breakdown of the rainbow of visible colors. We've got reds, orange, green, blues, and purples up there. And from an electromagnetic spectrum point of view, and why we see different colors, is those waves have different properties. We define those properties using terms like frequency and wavelength. Everybody heard those terms before? Most of us probably have. Frequency describes how often a wave repeats itself per unit time, often per second is the unit of time there. So really fast waves have a high frequency, really slow waves have a low frequency. We also have wavelength, describing the distance between each wave, the peaks of each wave or the bottoms of each wave. And so we could isolate the red color here, which is known as having very long wavelengths and low frequencies, and the purple, the violet, having a short wavelength and a high frequency. You can see the distance between the waves there are different, and the number of times that wave cycles, its frequency is different. Thankfully, that lets us see colors of different shades, those different frequencies and wavelengths. That's what our eyes are listening to. All right, frequency and wavelength. We're going to use that going forward a lot. So let's get to the fun part. I'm going to introduce a few of our musicians. We've got Ashley Lewis. Why don't you guys come on up here? Go ahead and get settled. Ashley Lewis has brought her violin up. Casey Olson with his cello, and Lydia Conger with her electric bass. These guys are all weather geeks like me, and I was very lucky to have these guys at my disposal. I appreciate them practicing over the last couple of months, and we're also very fortunate to have James Coburn from the physics department here, and he has brought his software and his microphone that is going to listen to the sound waves that the instruments are playing, and we're going to visualize them up there for you. So I'm going to switch over to his laptop. All right, so while these guys get set up and ready to go, and while James gets set up and ready to go, I will ask that we try to keep our talking to as little as possible, because we've got a really excellent microphone up here that will pick up just about everything. And so I will even try to shut up as much as I can so we can listen and watch the sound waves as best as possible. So to give you guys an example on what we're going to be watching, the top here represents the sound wave. Down here represents the frequency of basically my voice at the point right now. So we're going to be paying most of our attention to this waveform up here, because we're going to see how that changes based on the type of sound waves that are being emitted. And we're going to connect that with climate cycles afterwards. So we're going to start with the simple stuff. And Charlie, you want to come up and be our Vanna White? All right. James has brought a couple tuning forks in. Now, tuning forks are designed specifically to emit a specific, precise note. And you'll see why that matters here when we get the instruments playing. So watch this first note here. What note are we listening to here?
It's a C.
A C note.
A low C.
Now I want you guys to pay attention to what this looks like up there. I'll shut up and we'll let it do it again.
So I paused it there.
All right, we've paused it, so now we don't have to worry about me talking over it. So you can see the wave. Now let's drop to a different note. What's our next one here? A G. A little bit higher pitch. Now see if you can spot the difference in these waves. The higher G has a different wave with a higher frequency and a shorter wavelength. Now we could do this for a lot of different notes. That's about as pure of a note as we can monitor. Now we're going to complicate the waveform a little bit with an actual stringed instrument. We're going to start on the low end. Lydia, are you good to go? All right, she's got her electric bass. She's got the low notes. You guys see a difference? That low note has a much longer wavelength and a much shorter or much longer frequency. All right, Casey with the cello, he's going to be our mid. Does that look like the tuning fork? It's messy. Anybody know what that is? In a string instrument, and most sounds in nature have other notes being played behind it. Anybody heard of harmonics or overtones? He's playing a single note based on his fret, but we're hearing alternate notes underneath of it. So our waveform has a bunch of different frequencies together. It's messier, it's noisier. It's not as pure as the tuning fork. All right, let's see the high frequency ones here. A lot more wiggles, compacted shorter together. Our shorter frequency from the high notes that Ashley just played looked way different than what Lydia played with her electric bass. That's a demonstration of the differences in frequencies, or the number of cycles that those waves go through each second, and the wavelength of those notes being played. All right, you guys ready to make this fun? I've asked these guys to practice a chord because chords sound pretty. We're going to hear what happens when they all play a chord of different notes together and all of their frequencies line up and harmonize together. You guys ready? A nice, pleasant sound. You might even pay money to somebody to hear that kind of music played somewhere. It's free tonight, though. But you can see down here, in all the frequencies being played, we have lots of different notes sitting inside of that chord. That's the harmonics and the overtones that their string instruments are emitting. It's what makes that sound pleasant to our ears. Now I'm going to ask them to do something that you wouldn't pay for, and that is to play a dissonance chord. Now it's horror movie season, and that's the kind of music they put in horror movies because it kind of puts you on edge. You don't like to hear it. It makes you a little uncomfortable. That's because the sound waves that they are playing together do not harmonize. They interfere with each other. They call it dissonance. All right, you guys ready for the fun part? This is what they've been practicing for the last couple of months. They've been practicing what song? Or should we tell them or just let them guess? All right, we'll tell them afterwards. No spoilers. I've asked them to play about maybe a minute and a half, 2 minutes of a song. They're actually going to play the full song on the way out when you guys are ready to leave, so you can get a little bit of a concert on the way out. But right now, we're going to be able to watch as they play one of my favorite songs. You guys ready? Who knows the song? Back in the back. Yeah. Was that it? Coldplay. I love that song. Thanks, guys. I appreciate it. These guys, they don't know yet, but I'm volunteering them to play for weddings. They will charge you. Perfect. Thank you, guys. I appreciate it. And again, they'll play the full song on your way out of here. And thank you, James, for bringing that in. That made this work very well. Thank you. Give James a hand, too. All right. Let's teleconnect the dots here on the way out. There's a symphony of these climate teleconnections playing out across the planet every year. The Madden-Julian oscillation is a very high frequency. It takes about 60 to 90 days for it to complete its cycle. It's a very high frequency. That's like the violin. We have the ENSO and the North Atlantic oscillation. Those are more like the cello. It takes them maybe 4 to 5 years to complete their cycle of going in and out of their hot and cold phases. We have longer ones like the quasi-decadal cycle, which takes 10 to 12 years to complete its cycle. It might be a little bit more of the high notes on the electric bass. And we have the Pacific decadal cycle, which can take many decades to complete its cycle. That's like the really low bass notes being played. There's a whole symphony of these climate teleconnections playing out at any one given time. And all of them are cycling between their phases together, individually influencing the jet stream, but together collectively the jet stream is responding to all of them in general. So I've got one video here that hopefully ties everything together. This is something called a pendulum wave. I stumbled upon this about a month ago on Reddit, and it was a perfect example for this. So to let you guys have some prime understanding before we get into this, what's going to happen is this guy has created this pendulum wave, and he's going to release all these billiard balls at once. And the billiard balls at the top of the screen have a shorter string, and so their pendulum swing has a shorter frequency. It takes less time for it to complete its cycle. The balls, as you get closer to the bottom of the screen, have a longer string, and so their pendulum swing takes longer. And so these are going to be like our climate teleconnections. And so I've added some annotations on the top and the bottom, and so as these things swing back and forth, imagine and pretend in your head like each one of those balls is a teleconnection cycling back and forth between its cold and its warm phase, influencing the wet and the dry phases and cycles of Utah's climate. So we'll go ahead and get this started. The thing with having different frequencies is that sometimes it's very chaotic. Other times it's very beautiful and everything works together. So I'll let you guys just watch this play out. You can watch individual billiard balls and see how they're swinging versus the others. So imagine this playing out over decades and climate cycles swinging back and forth. Sometimes none of them are in the cold phase, sometimes all of them are in the cold phase, and vice versa. Each of them operates individually, but collectively, they can either be very chaotic or together, harmonizing or interfering with each other. They will eventually all meet back to the point where they're all swung on one side, just like how they were released. There they go, back to the beginning. I think that's a great way of demonstrating how all of these are working independently but together, each one of them influencing the jet stream, influencing the storm track, and influencing the weather and climate in a given region. Let's recap. Every season is unique. It's rare to get a normal year, usually one side or the other. And that's a function of the symphony of climate cycles operating across the planet, influencing the jet stream across each hemisphere. That changes the weather patterns on any given year. It also makes things very complicated to predict what a given year will look like. There's also inherent chaos of the weather system. That's the fun part about being a meteorologist and a climate scientist, is learning the science, understanding the physical world, and then trying to predict. And we're pretty excited when we get it right half the time. But just like sound waves with different frequencies, these climate cycles can harmonize together. And when we get a couple of these climate cycles all pushing the jet stream in one direction, we can have really extreme years. Weather can get pretty crazy. Or they can interfere with each other, which is the worst nightmare for us when we have one cycle pushing us in the dry phase, another one pushing us in the wet phase, and we're like, we'll be wrong no matter what. Thank you guys for spending your evening with me. I have one final wave. That's my wave goodbye. Appreciate you. Stick around afterwards. Enjoy all the demonstrations. And if we have a couple of questions, I'm happy to ask them in front of the audience, and I'll stick around as well.
I'm going to help you ask these questions. So if you have questions, just get ready. We have a device that will help you to do this. Do you know how to do it? What we're going to do is there's going to be a box with a microphone in it you can speak into for your question. We'll just toss it to you, and you just talk into the top of it.
Hey, any questions?
We have one in the way back.
Okay.
Our prediction for this winter. All right, we're loaded right out of the gate. Thank you very much for that. I mentioned the quasi-decadal oscillation, the QDO, early on when we had our teleconnection soup. That is statistically the most useful climate teleconnection we have. For about 6 of the last 7 years, we are in the dry phase, and it pushed us into the most historic drought we've observed in Utah. Last year, based on the cycle that we expected, was about to transition back into the wet phase. We had no idea, no predictability that would be that snowy last year. But that gives us a good indication that that cycle has flipped and we're back into the wet phase. So that takes about 4 to 5 years of wet to dry. You saw in that precipitation cycle we had, there's a couple of years that are all together in those phases. So our expectation, our official prediction is that collectively over the next 5 years or so, we will be in the wet and snowy phase. But that doesn't mean that every given year in that 5 years will be wetter, because we have the whole symphony playing out. We've got a very strong El Nino occurring right now into the winter. It doesn't push our weather and climate too much. Southern Utah has some relationship there, northern Utah not as much, but it will be affecting the jet stream and the storm track. And so right now we are leaning towards an above average winter. And so, yeah, we're hoping the snowpack is really positive again, because we need as much water as we can going forward. Yeah. You guys can follow this up in the springtime, and we see how it all evolved. Got one back in the corner, and then I see a hand up. We'll get to you in a second. Yeah, great question. So if you couldn't hear, talk about not harmonizing. If you couldn't hear the question, it was about how is climate change and global warming affecting all of these? And that's a huge concern in the climate science world right now, of our understanding of how El Nino, for example, influences global weather. We're getting new flavors of these things that don't look like anything we've seen in the past. And that makes an already tough to predict thing even more unpredictable. And so there's a potential that new climate cycles could emerge, that old ones will evolve. And so those interactions need a great deal of study and investigation before we have an understanding of it. But it's not making our life any easier, I'll tell you that. We had a question just behind you. She had her hand up just a little bit ago. That was it? Thank you.
Yeah, thank you so much. Are you able to explain to us what causes the jet stream?
Yeah, good question. So the jet stream, we call it a thermal wind in the science community, which is a term that, again, is not on the quiz after this, but it describes the fact that the winds are a function of temperatures. So the equator is very hot, the poles and the high latitudes are very cold. And where those air masses butt up against each other, where we get hot air really tightly compacted against cold air on a continental scale, is where the jet stream forms. It's responding to a very tight temperature gradient at the surface. And as you go above the surface, those winds increase. And so, yeah, this graphic way back here at the beginning, thanks to the broadcast meteorology world, you can see how the jet stream snakes in between those air masses of the hot and the cold air. And so it's that tight compaction of those temperatures, a very different temperature, that creates the jet stream. The jet stream is part of the natural system trying to balance out the temperature differences across the latitudes of the planet. So it will always be moving. Good question. Yes, sir.
Intelligence affecting what you do, getting more precise, making it more difficult to...
Yeah, that's a great question about artificial intelligence and how computing can help with a lot of this. And there's a huge push over the last 10 years for machine learning and artificial intelligence to help sort out these patterns. Historically, climate scientists have used sound wave processing. So a lot of the same things that are happening in a speaker amplifier from a technology point of view are used to understand the cycles and find patterns. Machines are much better at that. And so there's a new growing field and industry in climate science, science in general, to use machine learning and artificial intelligence to better filter out these patterns and help us see them. It's foreign to me, though. I'm lucky if I can get Venmo to work on my phone at the farmers markets. Any other questions? I'll stick around if you want a more personal question instead of getting a brick thrown at you.
So I'm having a barbecue this weekend, and it's going to be pork, not too spicy. What hot sauce would you recommend?
And the shameless self-promotion opportunities. I have to sign a conflict of interest, I think. I would go with my honey chipotle, I think.
Okay, thank you.
On sale for all Science Unwrapped people.
Thank you, folks. I appreciate it. Have a wonderful weekend.